The conduction electrons in a metal are free to move around, so we can think of the electrons as if they're in a box. And when the electron encounters the edge of the metal, it cannot get out because of a potential barrier. So below is an illustration of the energy associated with our conduction electrons. So down here would be the conduction electrons, and here would be the edges of the metal. And so when an electron encounters the edge here, it cannot get out because it would require an additional amount of energy to go over this barrier, and that energy is referred to as the metal work function, and the symbol is phi sub m for the metal work function. And typical metal work functions are on the order of 4.2 to 5.3 electron volts. One way for an electron to gain enough energy to be emitted from a metal is by shining light on the metal. So the light will be absorbed by the electron, and if the amount of energy gain is enough to overcome this potential barrier, the metal work function, then the electron can be ejected from the metal. So on the energy band diagram, it would be an electron gaining energy from the light, and the energy being such that it can get over this barrier and be emitted into the region outside the metal. This emission of electrons from a metal on which an electromagnetic wave is shining is referred to as the photoelectric effect. The behavior of the emission presented several puzzles that could not be explained with classical physics. So here is our metal, and we're shining light on it, an electromagnetic wave at some single frequency or wavelength lambda. So the electrons absorb energy from the electromagnetic wave and emit into the vacuum. Now if we have a second metal over here and connect them, what will happen is that a current will flow. So the electron flowing from the metal on the left to the contact on the right will be a current flowing through our circuit like this and across our gap this way. Okay, so this is actually similar to what happens inside a solar cell. Now, the electrons are coming off with some range of, say, kinetic energies. So with a variable voltage source here, we can increase the voltage until we have a potential barrier that shuts off the photocurrent. And that's illustrated in the diagram down here. Now, from a classical physics point of view, one would think that increasing the intensity of the light would increase the kinetic energy of the electrons and hence increase the voltage required to shut off the photocurrent. But that is not what was observed. It was observed the exact same voltage, and hence the same potential barrier was required to shut off the photocurrent. The photocurrent would increase with the intensity of the light, indicating more electrons were being emitted. But the maximum kinetic energy of the electrons being emitted was the same regardless of the intensity of the electromagnetic wave. Another puzzle with the photoelectric effect was the behavior with the frequency of the light. For a given metal, there was a minimum frequency before a photocurrent would be observed, and that frequency depended on the metal. Further, as the frequency increased beyond the frequency where you first observed a photocurrent, the voltage required to shut off the photocurrent increased linearly with the frequency. So in other words, the maximum kinetic energy of the electrons coming off the metal increased linearly with the frequency of the light. And the slope of that maximum kinetic energy versus frequency was called the Planck's constant and has a value of 6.63 times 10 to the minus 34 joules seconds. The photoelectric effect required a new non-classical explanation, and Einstein provided this explanation. He said that the energy in a beam of light is quantized, and the size of that quantum depended on the frequency. So in other words, the size of the energy quantum in a beam of light was equal to h times f, where h was our Planck's constant and f is the frequency of the light. Okay, so looking at the results of the photoelectric effect for the maximum kinetic energy as a function of frequency, let's extend the line down to where it intersects the energy axis. Okay, so for a frequency of f, the energy in a quantum of a beam of light is h times f. So until the size of the quantum was equal to the metal work function, an electron could not be emitted. And when the size of the quantum was greater than the metal work function, the additional energy in the quantum appeared as the kinetic energy of the emitted electron. This wave-particle nature of an electromagnetic wave can be illustrated with a double-slit experiment. Thomas Young first performed the double-slit experiment in 1801 to determine if light was a particle or a wave. So he had a light source and a screen with two slits to let the light through and a photographic plate. So when he covered the bottom slit so that light was only going through the top slit, the exposure on the screen was this one right here. Okay, and then when he closed the top slit and opened the bottom slit, the exposure he observed was this one right here. And so if light was a particle, when he had both slits open, the resulting exposure on the screen should be the sum of the ones from the individual screens, or something like this. But what Young observed was an interference pattern on the photographic plate. Looking at a point on our photographic plate, we see that the distance the electromagnetic wave has to travel if it's coming from slit 1 is different than if it is coming from slit 2. And when this path difference is an integer number of wavelengths, we will get constructive interference and a bright spot on the photographic plate. When the difference that the light has to travel is an integer plus a half times the wavelength, we will get destructive interference and a dark spot on the plate. That's what leads to these bright and dark fringes that Young observed, and he concluded therefore that light was a wave. Today we can lower the intensity of an electromagnetic wave such that we have HF joules of energy per second going through our double slit apparatus. So every second what we will see on the photographic screen is a dot appearing. And so every second we get a dot, and over time these dots are going to build up until they form these light and dark fringes. So this experiment is illustrating the wave-particle duality. The particle part is this exposure occurring every second by a particle which is referred to as a photon. And the wave part of the electromagnetic wave guides where these photons are going to hit on our screen.